So my name is Rand, and I'm going to be talking about private smart contracts using homomorphic encryption. So on a blockchain today, everything is public. We need things to be public because we need to agree on what state is being computed. So this creates a bunch of issues around theft, surveillance, MEV, which fortunately we can solve with a new technology called homomorphic encryption. So the idea of homomorphic encryption is that you can compute on data without actually having to decrypt it. So this is great because it means that you can have encrypted transaction data, encrypted state updates, encrypted on-chain data, which opens up a bunch of really cool use cases, such as trusted bridges, where you can do homomorphic signatures on-chain, blind auctions, where the NFTs and the amounts being bid is not known, confidential voting, where the tokens used for voting in the DAO are basically not revealed. Basically, FHE is for privacy what ZK has been for scalability, and when you combine the two, you can actually have some scalable private blockchain protocol. The important thing about FHE to keep in mind also is that it guarantees data availability because the data is actually kept on-chain at all times. Contrary to ZK, you don't have to do the computation off-chain, you can actually do everything on-chain. So how does FHE work? Basically what you do is that you encrypt some data and you have to add some random noise to the data. Because you're adding this random noise, you basically also have a growth in the noise itself when you're computing on the encrypted data. For example, if you're adding encrypted values, the message itself is growing, but the noise as well, which means that after some point, you're basically getting noise overflowing on the data, which gives you an incorrect decryption. So this is a problem in a smart contract because if you don't actually have the ability to do infinite number of operations, then eventually, for example, in a balance transfer, you would have an incorrect result of the FHE computation. So the way we solve that is through something called bootstrapping, which is a special mathematical operation where you can basically clean up the noise so that you can keep on computing forever. And bootstrapping is the reason why FHE is slow today. The other problem with FHE is that if you can only do encrypted additions and multiplications, how do you compute the comparisons and the nonlinearities that are needed in a contract? If you have to use a polynomial approximation to compare values, you're not going to end up with a correct result every time. So for this, you need to use a new technology called TFHE, which enables you to do encrypted arithmetics, but also encrypted table lookups. And table lookups are super important because they basically give you the capability to compute any function without any approximation. The only thing that we're still missing today is speed. So even though we've made FHE 20 times faster in the last couple of years, we really need ASIC acceleration to make this go 1,000 times faster. So it works great today. You can do a few transactions per second, but if you want 1,000 TPS, you're going to need hardware acceleration, which is coming in 2025. So FHE is basically a done deal in a couple of years. So how do we use that for private smart contracts? Well, what we want is a simple user experience, a simple developer experience, and a simple integration for blockchains. What we created is a set of precompiles that augment the EVM with those extra FHE data types that you can basically use, for example, here in your ERC20 contract without changing the way you write your contracts. So just replace your integers by encrypted integers, and then you're basically done. The unique thing here is that you also have now encrypted values on chain, so you have to also decide who's allowed to decrypt which value. So you need to add some extra level of access control logic, which is being solved by effectively decrypting the value for the user based on some condition in the smart contract. There are a few technical challenges. First, because we want composability, it means that all the data on chain is encrypted under the same key. If it's encrypted under the same key, who has the private key for decryption? The second problem is performance. How do we increase throughput while keeping block sizes small, considering that homomorphic encryption has a very big expansion factor versus plain text data? So for securing the private key, we basically use threshold cryptography, where we split the private key of the network into a bunch of nodes, which need to agree at least 2/3 to decrypt in order to get a correct decryption. So this guarantees that nobody actually has the decryption key. To avoid people copying data from the blockchain that's encrypted and writing a contract to decrypt it, we also provide zero knowledge. We also have to provide a zero knowledge proof when you're sending a transaction that are encrypted so that we're sure the user knows what he's doing. So finally, the next thing is how do we go from 5 to 1,000 TPS? First, we need trend ciphering. So we need to basically go from a very compact encryption scheme like AES and turn that into FHE. So this would allow you to have block sizes which don't expand in size even though the inputs are encrypted. The second thing we want for scalability is FHE rollups. So we could do optimistic rollups today. I think we could work today. I mean, today, like soon. But really, what you want eventually is ZK FHE rollup. So in this particular case, you don't care about the zero knowledge part of the ZK rollups. You care about the verifiability part. So what you want is verifiable FHE, because if you do that, you can basically have infinite scalability while keeping all of the data encrypted. And finally, as I mentioned, hardware acceleration, which is coming very soon. So this is not hypothetical. This is something that we've announced a year ago that we were working on. And even though today homomorphic encryption isn't the fastest technology, it actually works. And it works so well, in fact, that we are going to be releasing a testnet at ECC this summer where you're going to be able to build homomorphic smart contracts using a normal EVM environment and basically start testing it. So Zama isn't going to be launching a chain. There is no such thing, but we want people to start understanding that this technology works and to start basically thinking about all kinds of different use cases for it. So if you want to access it, zama.ai/testnet. Thank you.